All right, great. This morning we are going to be working to solve these exponential and logarithmic functions. We're actually going to solve. We're actually going to find out what the x variable is. Now, remember, what makes an equation exponential? X in the exponent, absolutely. Exponential equations are equations with variables as exponents. X has to be in the exponent. Now, a couple properties here. Property of equality for exponential equations. All right, if b is greater than 0 and b can't be 1, okay, remember b is the base of the exponent, then b to the x equals b to the y, if and only if, goes both ways. X equals y. There should be nothing shocking about that. If my bases are the same, their exponents have to be equal. We have been using that for several days now when we were talking about the definition of a logarithm and writing it in exponential form. That should make sense. When the bases are the same, the exponents are equal. So for example, this is going to be exciting. If 4 to the x is equal to 4 to the 9, what can I say? You bet. Then x equals 9. All right, now, going to be a little bit more challenging than that. So, taking a look at example number A, letter A, example of letter A, 3 to the x is equal to 1/9 of the fraction raised to the x plus 3 power. All right, so here's the deal. Any thoughts on what we're going to do? X is in the exponent. These are exponential. I really want the bases to be the same. Any way that I can make that happen? Come on, people. You bet. 9 is 3 squared, and 1/9 is 3 to the negative 2. We should be getting there. 3 to the x is equal to 1/9. I can write as 3 to the negative 2, all raised to the x plus 3 power. Now, just a question. All right, Brooke, a power to another power, what do I do with my exponents? Multiply. So this is 3 to the x is equal to 3 to the negative 2 times the quantity of x plus 2. All right, should not be earth-shattering. When my bases are the same, that means that my exponents are equal. So that means that x has to be equal to negative 2 times the quantity of x plus 3. So x is going to be equal to negative 2x minus 6. 3x is going to be equal to negative 6, and x is negative 2. When my bases are the same, the exponents are equal. All right, now let's take a look at b. b is a great one. 4 to the x is equal to 11. All right, 4 and 11 are my bases. What do they have in common? Absolutely nothing. 4 is 2 squared, 11's prime. He's not going to be a perfect square, a cube, or fourth power of anything. So, we know in algebra that there are many things that I can do to solve an equation, but many of those things, if I apply something to one side of my equation, I needed to do it to both sides of my equation. All right. Now, here's an interesting thing. Logs work the same way. Now remember, log functions are the what of exponential functions? The inverse. That works in our benefit. Think about that. If in an equation they add 7, what do I do on both sides? I subtract 7 from both sides. So, if I have x in the exponent here, to undo that, I'm going to apply the log on both sides. A log function is the inverse of the exponential function. Now, this is exciting stuff. That x, I can see him, he's taking off his glasses, he's putting on his cape. What's he going to do? He's going to fly out in front, absolutely. I now have gotten the ability to get x out of the exponent because I've applied that log to both sides. So x multiplied by the log of 4 is equal to the log of 11. All right, Brennan, now what?
I don't know.
What's going on between that x and that log of 4? Yep, so how do I undo that? Divide by what?
X times log 4.
Okay, what am I going to divide by? I want to get x by itself.
Oh, log 4.
Good. I'm going to divide both sides by the log of 4. That's going to cancel, so x is approximately equal to, all right, calculator game, people, you got no choice. Take the log of 11, divide it by the log of 4. What is it?
1.72.
About 1.7297-ish. Fair enough. Now, do I have any reason to get these wrong? No, because what can I do? Check. All right. So in other words, 4 to the 1.7297 power, what do you get? Pretty close to 11. It's not going to be perfect. We're rounding, but it's pretty close to 11. Does anybody have an issue with that? All right, fantastic. All right, Newton's law of cooling. Really an interesting application of these situations. Newton's law of cooling states that for a cooling substance with initial temperature T sub 0, the temperature T after T minutes can be modeled by this. I'm not going to ask you to memorize this equation. I want us to be able to use it. If I ask you for this on a quiz or a test, I will give you this equation. There's no need to memorize it. Where T sub R is the surrounding temperature, the temperature in the room around what's going on, and R is the substance's cooling rate. Every substance cools at a different rate. Okay, so looking at this situation, hot chocolate that has been heated to 90 degrees Celsius is poured into a mug and is placed on a table in a room with a temperature of 20 degrees Celsius. If R is 0.145, if the cooling rate of this substance is 0.145, when the time T is measured in minutes, how long is it going to take the hot chocolate to cool to a temperature of 30 degrees Celsius? The exponent is negative RT. Okay, I'll rewrite it for you right now. No need to panic about that. So T is equal to the quantity of T sub 0 minus T sub R times E, all raised to the negative RT power, plus T sub R. Hopefully that's a little bit easier to see.
I can't tell if you have T of E or just T times R.
In the exponent, this is negative RT. This is T equals T sub 0 minus T sub R times E to the negative RT plus T sub R. Okay, now, hot chocolate's been heated to 90 degrees. Any thoughts on where I'm going to put that? T? T sub 0. The initial temperature, it starts at 90 degrees. Perfect. It starts at 90 degrees. All right. Placed on a table with a temperature of 20 degrees Celsius. Okay. It's in a room that is 20 degrees Celsius. Where am I going to put that? T sub R. So in both cases, T sub R is 20. Okay. If R is 0.145, okay, so we know it's E to the negative 0.145, the cooling rate of hot chocolate. We'd have no way of knowing that if they did not give us that information. How long will it take the hot chocolate to cool to a temperature of 30 degrees Celsius? Where am I going to put that? T. The temperature at the end we want to be 30. And that means that I am solving for little t. It means I'm solving for little t. Okay, everybody good so far? All right, let's see here. Levi, what's the first thing you're thinking we could do? All right, parentheses, so 90 take away 20 is going to be 70. E to the negative 0.145t plus 20. Perfect. Connor G, where are we going from there? I like it. Let's subtract 20 from both sides. 30 take away 20 is going to be 10 is equal to 70. E to the negative 0.145t. Perfect. Katie, what about now? Divide both sides by 70. So 10 divided by 70 is going to be 1/7 equal to, my 70s are going to cancel, and I have e to the negative 0.145t. Perfect, perfect, perfect. All right, now, does anybody have a thought on what we want to do at this point? I need to get the t out of the exponent. Can I make the bases the same? I want to get t out of that exponent. Can I make the bases the same? Can I make 1/7 have something in common with e? No. So what is the only method that I have now showed you to get the variable out of the exponent? Lexi? All right, nice. What we did in the last one is we took the log on both sides, right? We took the log on both sides. But notice, what is special about this problem? What is in there? E. So instead of taking the common log, instead of taking the log base 10, it would make most sense to take ln because it already accommodates for that e. So I'm going to take the ln of that fraction of 1/7 is equal to the ln of e to the negative 0.145t. All right. Daria, what happens now?
Negative 0.145t goes to the front.
Good. The negative 0.145t comes out in front. So the ln of 1/7 is equal to negative 0.145t times the ln of e. Now I got a question for you. What's the ln of e? Okay, because what base am I in? I'm in base e. What's my exponent here? A 1. So really it cancels and becomes 1. The ln of e is always 1. Okay. Perfect, perfect. Andy, what do you think we should do now? Good. Divide both sides by negative 0.145. So t is approximately what? All right, calculator is your best friend. What's the ln of a 7th? And then divided by negative 145 thousandths. Good. About 13.42 what? What is it exactly that I'm finding here? Minutes. Perfect. So far, so good? We okay with that? All right. Now, here we go. Logarithmic equations. Logarithmic equations are equations that involve logarithms of variable expressions. Logarithmic equations have to have logs in them. All right. Now, something that will help us in solving these. If b, x, and y are greater than 0, b can't be 1 or we got issues, then log base b of x is equal to log base b of y if and only if x is equal to y. If I'm taking the log on the same log on both sides, the only way they're going to be equal is if they're arguments, if what is inside is equal. So for example, if log base 3 of x is equal to log base 3 of 12, what's got to be true? If log base 3 of x is equal to log base 3 of 12. Yeah, absolutely. I'm taking the same log on both sides, so my x has to be equal to 12. Okay, let's take a look at these. All right, so I have log base 4 of that group of 2x plus 8 is equal to log base 4 of that quantity of 6x minus 12. If I'm taking the same log on both sides, the only way that these two logs are going to be equal is if they're arguments, if what is inside is equal. So that means that 2x plus 8 has to be equal to 6x subtract 12. All right, Leslie, what do I do first? Add 12. So 2x plus 20 is equal to 6x. Then what? Subtract 2x. So 20 is equal to 4x. And x is what, folks? X is 5. All right, now, in letter B is an unusual or a different type of situation. In this case, I only have a log where? On one side. I only have a log on one side. Now remember the definition of a logarithm. In this case, we need to remember the definition of a logarithm. When I'm finding a logarithm, I'm finding what? The exponent. Got a question for you. In this case here, what is the exponent? I heard it. What is the exponent? How would I rewrite this? All right, my 7 will scoop up the 2, and it's equal to what's inside. What is my exponent? 2, absolutely. Now, when I have a single log, the best way to solve these is to write them with their exponent, to change it over to exponential form. If I have a single log, does that make sense? If it is a single log, you want to write it with an exponent. So 7 squared is 49, equal to 3x minus 2. If I add 2, 51 is equal to 3x, and x is 17. All right, now, one drawback of these, and I know that this can be painful, but they certainly have the possibility of creating extraneous solutions. Extraneous solutions are what? Extra answers that don't really work. They are extra solutions that do not really work in the original equation. And how do we get them? Yep, we've gotten them in cases where we've had to square root both sides of an equation. In this case, we get them in situations where logs are involved in our solving process. How do we make sure we get rid of them? We got to check. We've got to do a check. Okay, so let's take a look at one more situation. All right, somebody have a thought on what we can do there in number 4? Anybody have a thought on what we can do there in number 4? Or how is this different than the ones that we've looked at so far? Okay, we have 2 logs, but they're on the same side. We have 2 logs, but they're on the same side. On the other side, I simply have a number. Remember, when you're finding a logarithm, you're finding what? An exponent. Keep that in mind. Now, my logs are on the same side of that equation. What is happening between those logarithms? Addition. Is there anything I can do with that? How can I condense them? I can multiply those. Absolutely, I can put them together. So log base 6 of my first argument, 3x, multiplied by my second argument of x minus 4 is equal to 2. All right, does anybody have a suggestion at this point? Yes. Absolutely. I have a single log on one side. I need to remember what the definition of a logarithm is. When you're finding a logarithm, you're finding an exponent. I'm going to write it with its exponent. So 6 to the second power is equal to what's inside, which is 3x times the quantity of x minus 4. All right, 6 squared is 36, is equal to 3x times the quantity of x subtract 4. All right, let's see here. Miss Jocelyn, you got any thoughts on what we want to do? All right, let's distribute. And then what? Beautiful. Let's subtract 36. Let's get everything on one side equal to 0. Because what am I thinking would be a smart idea with this? Absolutely. All right, what are we going to do to factor this thing? All right, what's my GCF? What's the GCF? 3. And I'm left with x squared minus 4x subtract 12. Then what? Beautiful. We're looking for two numbers that multiply to negative 12 that add to negative 4. Tessa said they're negative 6 and 2. Because my coefficient in front of x squared is a 1, I know that I can say x minus 6 times x plus 2 multiplied by that GCF of 3 is equal to 0. All right, Brody, now what? All right, 3 equals 0. Never. X minus 6 is equal to 0, so x is 6. X plus 2 is equal to 0. X is negative 2. All right, am I finished? No, we've got to check. You've got to do the check. So I'm going to walk you through this check just to make sure everybody knows what they're doing. All right, my check of x is 6. Go back to the original equation. So log base 6 of 3 times 6 plus log base 6 of 6 minus 4 better be equal to 2. Okay, so log base 6 of 18 plus log base 6 of 2 better be equal to 2. All right, these are being added. The two logs are being added, so I know that I can multiply. So log base 6 of 18 times 2 is equal to 2. Well, log base 6 of 36 is 2. Oh yeah, 6 squared is 36. All right, x equals 6 is a good one. All right, let's do our next check with x is negative 2. So log base 6 of 3 times negative 2 plus log base 6 of negative 2 minus 4 is equal to 2. Now, here's the deal. I can never take the logarithm of what type of number? I can never, ever, ever take the log of a negative number. So the minute that I see that there's going to be a negative number in here, and in addition, there's actually going to be a negative number in here, it doesn't matter if it really works or not. I cannot take the log of a negative number, so I've got to throw negative 2 away. My solution is only x is positive 6. Do you have any questions? Okay.